We are jumping straight into the zero fluff summary for this episode of AI Paper Slump. Because, well, if you try to peek inside the brain of the newest self-teaching AI, you are not going to find English reasoning.
No, definitely not. You're going to find this fragmented alien gibberish that somehow makes the model infinitely smarter.
Right, which is just wild. And that is the core takeaway from today's paper. It's called Latent On-Policy Self-Distillation, or LOPD by Zhang et al.
Yeah, and the core problem they're tackling here is that on-policy self-distillation, or OPSD, is super effective for, agent evolution.
Exactly.
Yeah.
But the current methods rely entirely on handcrafted, really rigid, privileged context for the teacher model, like textual answers or these verified reasoning traces.
Right. And the solution LOPD brings to the table is basically replacing that handcrafted text with a learnable, end-to-end, continuous latent substrate.
Which is a mouthful, but basically retrieves past raw experiences and compresses them into latent tokens that guide the self-teacher.
Yeah. And the secret sauce making all of this actually work is this privileged margin objective.
Right, because that forces the teacher to maintain a verifiable advantage over the student, so the teacher doesn't just lazily copy the student's distribution.
Exactly. And honestly, the results are staggering. I mean, LOPD dramatically outperforms standard OPSD, GRPO, and SkillSD on both tool use and coding benchmarks.
Yeah, of course, Qwen 3 and OMO 3 backbones. Right?
Mm-hmm.
Yep.
And it achieves higher performance using less than 30% of the standard rollout budget.
The 30% number is, honestly, it's the real headline for anyone who is managing a compute budget right now.
Mm-hmm.
It's just a fundamental shift.
It really is. I mean, the standard approach in the field has always been to just obsess over the textual artifact.
It's like constantly asking, what specific string of English text should we feed the teacher model so it can properly guide the student?
Exactly. And LOPD just completely flips the script and asks, why are we forcing the model to read human language at all?
Right. Why not just let the network learn its own optimal mathematical representation of its past successes?
Yeah, and to understand why bypassing human language is such a massive breakthrough, we really need to look at why those existing OPSD methods eventually hit a brick wall.
Oh, for sure. Because if you haven't built one of these pipelines recently, the standard on-policy distillation setup is basically designed to have a student model learn from its own generated trajectories.
Right. You do this to avoid distribution shift, which is, what happens when you train a model on data generated by a completely different and usually much larger oracle model.
Yeah, so in the OPSD paradigm, you just eliminate that separate oracle entirely. The student and the teacher are actually instantiated from the exact same model weights.
Exactly. And the student is basically tasked with generating a trajectory based purely on the current state and its interaction history.
It's just guessing its way through the problem, basically.
Pretty much, yeah. And then the teacher steps in to reevaluate those exact same visited states. But to make the teacher smarter than the student, you give it what we call privileged context.
Right. And historically, that privileged context is human designed. So it might be the ground truth answer, or a verified reasoning trace, or explicit feedback from the environment.
You basically hand the teacher the answer key, so then it can provide better next token probabilities.
Right, and then you train the student to mimic those sharper probabilities using a reverse KL distillation loss.
Yeah, that's a theory anyway. But the empirical findings in this paper expose a pretty major flaw in that exact logic.
Yeah, because handcrafted context is not universally optimal at all. In fact, it can be incredibly destructive, which I have to admit, when I first read that, I was genuinely confused.
Oh, totally. It feels like a paradox.
Right. Because if the teacher has access to a verified reasoning trace or the actual ground truth answer, isn't that universally a good thing?
Mm-hmm.
How can giving a neural network extra verified information actually hurt its ability to supervise?
Yeah, I mean, it doesn't make sense until you look at how fragile specific context formats are across different learning states. The paper highlights this method called SDPO.
Oh, yeah, where it conditions the teacher by feeding it successful sibling rollouts.
Exactly. And the authors applied SDPO to a vanilla Qwen 3-4B model on the BFCL v3 benchmark, which, measures complex tool use.
And the performance didn't just plateau, it completely collapsed. I mean, it dropped from a baseline of 22.88 all the way down to 15.75.
Which is just a catastrophic drop for a method that is supposedly adding helpful context.
Seriously.
Yeah.
And we see a similar degradation with standard OPSD on the live code bench dataset too, right?
Yeah, injecting a fixed Oracle trace actually lowers performance compared to just using the unadapted backbone. It's crazy.
What's actually happening there?
Well, the root of the problem is that a context format that acts as a brilliant hint in one specific regime becomes like mismatched or sparse or just overly prescriptive in another.
Ah, okay. So if the teacher is handed a highly specific Oracle trace, that trace represents just one valid path to the solution.
Right. But it might completely clash with the specific trajectory the student is currently exploring.
Oh, I see. So it forces the teacher to try and drag the student toward a specific style of solution rather than just helping the student refine its own current thought process.
Exactly.
Okay, let's unpack this with an analogy because this is fascinating. It's kind of like having a humie teacher who only knows how to give one specific type of hint.
Yeah, like their only teaching method is to just blurt out the final answer.
Right. And if a student is stuck on step 2 of a 10-step math problem and they just need a slight nudge on how to carry the one or whatever, blurting out the final answer is completely useless.
Yeah, it doesn't help at all.
The format of the hint is dictating the learning rather than the student's actual needs dictating the format of the hint.
Exactly. The current paradigm forces the AI's experience into this discrete, human-readable artifact. But that relies on a huge, unsubstantiated assumption
Which is,
that we humans actually know the best way for a language model to internally process its own past experience.
well, yeah, and LOPD just abandons that assumption entirely. It makes the privileged context itself end-to-end learnable.
Right.
Which brings us to the actual architecture of this latent substrate. Because if handcrafted English hints are too rigid, how does LOPD actually make them flexible?
Yeah, how do you pull experience out of a model's past without writing it down as text?
Exactly.
So the system starts by maintaining a very lean offline experience bank. They aren't storing elaborate, verbose textual reflections or, big chain of thought summaries.
Okay, so what are they storing?
They just store successful trajectories as really compact action result traces. It's stripped down to the raw mechanics of what actions the model took and what the environment returned.
Ah, so it's omitting all the unnecessary conversational fluff.
Totally.
But when the model is faced with a new task, how does it know which of those raw traces to look at? I mean, it has to find the right one somehow.
Right, so it uses a dense retriever. Specifically, they utilize the Quenin3 embedding 8B model.
Okay.
It embeds the current task and pulls the top 3 most relevant past experiences from the bank based on cosine similarity.
Got it. But here is the critical divergence from prior work, right? Instead of pasting those 3 raw textual trajectories directly into the teacher's prompt.
Right. LOPD routes them through this novel mechanism they call the composer.
Yeah, and I found the composer diagram in the paper a bit dense, honestly. So let's break this down mechanically for everyone.
Sure.
The composer's job is to take that raw, retrieved text and compress it into exactly 32 continuous latent tokens. How is it doing that translation without losing the plot entirely?
Well, the composer actually leverages the frozen backbone of the model itself, but it attaches a trainable LOPD adapter to it.
Okay, so the NeuRA acts as an encoder.
Exactly. The retrieved experience is passed through this encoder, transforming the text into a sequence of hidden states. And then those hidden states are fed into a Q-former style compressor.
And the Q-former uses learned queries, right?
Correct. You can think of these learned queries as like mathematical searchlights.
Oh, I like that.
Through a cross-attention mechanism, these queries basically scan the hidden states of the encoded experience and pull out only the task-relevant procedural guidance.
And because this entire composer pipeline, so both the LoRa adapter and the Q-former, is fully differentiable, the system can actually update it using backpropagation.
Yes, that is the crucial part. The distillation loss from the student's training is flowing backwards through the frozen teacher network down into those 32 latent tokens.
Updating the weights of the composer itself.
Oh.
That is wild. The network is literally learning via gradient descent exactly which features of a past success are most useful to extract and pass to the teacher.
Right, it's dynamically learning how to hint itself.
That's so cool.
Yeah, so instead of deciding beforehand that the teacher needs an oracle answer or a reasoning trace, the composer might learn to extract, say, a specific syntactic pattern.
Or a sequence of API calls, maybe.
Exactly, or some abstract logical relationship that we couldn't even begin to articulate in English. It compresses that highly targeted guidance into a dense, continuous format that the teacher model can natively process.
Right, but, and here's where I saw a massive optimization risk when I was reading this, If the composer is jointly optimized with the student using a distillation loss, what stops the entire system from just collapsing?
Yeah, the classic collapse problem.
Right, because neural networks will always find the path of least resistance. And the objective is to minimize the reverse KL divergence between the teacher's distribution and the student's distribution. So isn't the easiest way for the composer to achieve a zero loss just to output completely useless latent tokens? Like tokens that basically tell the teacher to perfectly match whatever flawed distribution the student is currently outputting?
Like it would just agree with the student.
Exactly. The loss hits zero, the optimizer is thrilled, but the student learns absolutely nothing. It is like the ultimate lazy teacher problem.
And the authors directly address this vulnerability. Because you're right, joint optimization without constraints will always lead to that exact collapse.
So they tested this.
Yeah, they ran an ablation study where they removed their constraint mechanism, basically setting the margin parameter, lim, to 0.
And what happened?
The performance on the n-scalar benchmark plummeted to 0.551, which is actually worse than just freezing the composer and not optimizing it at all.
Wow, so unconstrained distillation gradients just degrade the latent context until it's completely uninformative.
Totally.
So what is the mathematical fix that prevents the teacher from just getting lazy and agreeing with the student?
They introduce what they call the privileged margin constraint. It fundamentally ties the teacher's token-level advantage directly to the actual outcome reward of the full trajectory.
Okay, break that math down for me a bit.
It relies on a super simple advantage function. If a trajectory is perfectly successful, the reward is 1. The formula doubles that and subtracts 1, leaving you with a positive advantage of 1.
2 times 1 minus 1. Got it.
Right. But if the trajectory fails, the reward is 0. Doubling that and subtracting 1 gives you a negative advantage of -1.
I see. So it literally translates a binary successor failure outcome from the environment into a positive or negative token level demand.
Exactly.
But how does that margin parameter actually come into play?
So the authors set a minimum privilege margin at AROA at 0.05. This dictates that if the student successfully completes a coding task or like a tool use plan, the teacher is strictly required to predict those successful tokens with at least a 5% higher log probability than the student.
Ah, okay. So it has to be noticeably better.
Yes. And if the teacher's advantage drops below that 0.05 margin on a successful trajectory, a massive penalty kicks in.
That is brilliant.
Yep.
The teacher is mathematically forbidden from just matching the student. It has to maintain its status as the expert.
Right. It basically has to say, yes, you generated the correct code here, but I was mathematically more confident in that code than you were.
And because the main backbone of the teacher is completely frozen, it can't just change its own weights to boost its confidence. Nope. The only way the teacher can meet that strict 5% margin is if the composer feeds it incredibly useful, rich, latent tokens that naturally sharpen its next token prediction.
Yeah, the elegant part of this design is really how the two forces balance each other out. The outcome-weighted privilege forces the composer to hunt for evidence that supports successful behavior, guaranteeing the tokens are informative.
While the reverse KL distillation gradient teaches the composer exactly how to format that evidence so the teacher can actually digest it smoothly.
Exactly. The lazy teacher loophole is completely closed.
Okay, so that covers the theoretical math, which is super elegant. But, for the systems engineers listening, theory often just dies in the deployment phase.
Oh, absolutely.
How do you actually implement this without writing custom CUDA kernels or completely breaking standard inference engines? Because we're talking about injecting continuous, non-textual floating point vectors directly into the middle of a standard large language model.
It sounds like a nightmare.
Right. How do you put this into production on something like VLLM or SGLang?
Yeah, deployment friction kills so many interesting latent space concepts. But the authors navigated this using a really highly practical placeholder strategy.
Oh, how does that work?
Instead of messing with the model's fundamental architecture, they just manipulate the chat template. They insert a standard text-level sentinel string into the prompt, literally just the character's latent pH.
So this is a regular text tag.
Exactly. The standard tokenizer processes the prompt and splits it around this sentinel. Then the system inserts dummy token IDs, just standard pad tokens, into the sequence.
And it inserts exactly the number of dummy IDs that correspond to the latent tokens, right?
Yep.
So if they retrieve 3 experiences and compress each into 32 tokens, they insert 96 dummy pad tokens.
Right. So to the inference engine, it just looks like it's processing a normal string of text with a big block of pad tokens in the middle.
That's so clever.
The engine goes ahead and embeds the whole sequence as usual. But right before that sequence hits the first transformer layer, LOPD uses a prompt embeds interface, which, by the way, is natively supported in VLLM and SGLang.
Okay, and what does it do with that interface?
It executes a simple tensor substitution. It just overwrites the embeddings of those specific dummy placeholders with the actual continuous latent tokens generated by the composer.
Wow. They just swapped the dummy tensors out for the real latent vectors right before the forward pass.
Yeah.
That means the backbone model requires absolutely zero architectural changes. You don't need to write custom attention masks or anything.
None at all. And most importantly, it is fully transparent to the engine's KV caching and batching logic, which means you don't destroy your inference speed.
That is huge.
Yeah, and the authors verified that this placeholder injection introduces basically no numerical artifacts compared to standard token forwarding.
And they keep the LoRa adapter separated too, right?
Exactly. They maintain a strict separation of concerns.
Yeah.
The LoRa is only active when the composer is encoding the retrieved experience. It is explicitly disabled during the main forward pass for both the teacher and the student.
So the model acts as a pure base actor that just happens to be conditioned on these injected, highly dense continuous embeddings.
That's right.
Okay, so we have the optimization theory and we have the production-ready systems engineering. Let's look at the actual empirical dominance, because the claims here are frankly massive.
They are, and the evaluations are really exhaustive. They tested LOPD across 3 different backbones, Quemin 3.4b, Hu1 3.8b, and Ulma 3.7b.
Yeah.
LOPD sweeps the board. It outperforms standard distillation methods like GRPO, SDFT, and SkillSD on complex agentic tasks like Nscaler, AceBench, and BFCLv3.
Which are notoriously difficult.
Yeah, and it maintains that dominance on pure coding benchmarks too, like Taco, Live Code Bench, and Evel Plus.
But I want to zero in on the sample efficiency metrics, specifically on that Nscaler benchmark, because the training dynamics graph in the paper is just wild.
It really is.
LOPD shoots past a 0.61 mean reward after just 320 on-policy generations.
Yeah.
And to put that in perspective for you listening, standard methods like GRPO and SkillSD take over 1,600 generations just to crawl near those numbers. LOPD is achieving state-of-the-art results using less than 30% of the standard rollout budget.
Right, and that persistent early separation in the learning curve suggests the latent teacher is functioning on a completely different level of efficiency.
How so?
It's extracting a vastly denser, higher quality learning signal from every single visited trajectory compared to traditional scalar rewards or, text-based distillation. Every rollout is giving the student a richer lesson.
Which is amazing. But the architecture forces every retrieved experience into exactly 32 tokens. Why 32? Did the sensitivity analysis explain why that specific bottleneck is the sweet spot?
It did. The authors systematically varied the capacity of the composer. If you restrict it to 8 or 16 latent tokens per experience, the composer is clearly bottlenecked.
Like it's trying to squeeze too much through too small a pipe.
Exactly. The information gets too compressed, and the reward on Nscaler just hovers around 0.56. But the moment you expand it to 32 tokens, the performance spikes to 0.637.
Okay, but what happens if you give it more room, say 64 or 128 tokens?
It just fluctuates without any monotonic benefit. The extra capacity doesn't translate to better supervision. It might even introduce noise.
Interesting.
And they found a similar plateau with the retrieval count, too. Pulling in more than 3 past experiences didn't systematically improve the aggregate scores at all.
So the optimized window is really tightly defined. It's exactly 3 retrieved experiences compressed into 32 tokens each for a total latent context of 96 tokens.
Yep, that's the magic number.
Well, the efficiency is undeniable.
Right.
But this raises kind of the classic AI evaluation question. Did the student actually learn to, quote-unquote, think better, or did it just find a clever way to overfit and hack the environment's reward function?
Right, which is the most important distinction in agent research.
Oh.
So to prove the student actually internalized better reasoning, the authors tracked fine-grained behavioral data on the Nscaler test set. This data is actually in Table 3 of the paper.
Cool.
And keep in mind, at inference time, the student model operates entirely on its own. The retrieval bank is gone. The composer is gone.
There's no latent context being injected at all.
Exactly. It's just the standalone, distilled student interacting with the environment.
And the data shows it behaves completely differently from the vanilla baseline model, right?
The behavioral shift is drastic. The LOPD-trained student uses significantly more environment steps to complete a task on average, 17.04 steps, compared to just 11.1 for the vanilla model.
But more steps.
Yes. However, it makes dramatically fewer tool calls per step, dropping from 3.50s down to 1.1.
Oh, wow. So it stopped behaving like a frantic novice.
What do you mean?
Well, the baseline model was basically spamming 5 speculative API calls at once, crossing its fingers, and just hoping one of them returns something useful.
Yeah, totally.
But the LOPD student behaves like a senior developer. It executes a careful, sequential, one-step-at-a-time plan. It looks at the state, makes a single precise tool call, waits for the result, and then plans the next step based on that.
Exactly. The first step response length actually dropped by nearly 40%, and repeated redundant tool calls practically vanished.
That's incredible.
And the reward per tool call increased significantly. This is definitive proof that the student truly internalized the procedural guidance from the latent teacher.
It didn't just curve fit the reward signal.
Right. It fundamentally adopted the sequential reasoning pattern that the composer had managed to extract from those past successful experiences.
So the outcome reward aligns the teacher, and the distillation process forces the student to permanently internalize that behavior.
Precisely.
Which is amazing. And that pretty much wraps up today's breakdown on AI paper slop. LOPD is a massive signal that we need to stop trying to handcraft experience formats.
We really do. We have to start letting the network learn the optimal representation of its own past.
Absolutely. But before we go, I want to leave you with one final, slightly provocative thought to mull over.
Oh, lay it on me.
So, in the paper's case study, the authors attempted to project those 32 latent tokens back into the language model head, just to see what the composer was actually, saying to the teacher. Figure 6 shows the translation.
Yeah, and the output was completely unreadable.
It was entirely alien.
Right.
It projected as this fragmented, multilingual, code-like gibberish. It wasn't an English summary of the task. It wasn't a standard chain of thought.
Nothing recognizable.
Right. So if the most mathematically efficient way for an artificial intelligence to teach itself complex procedural tasks is through an alien, non-human readable latent language, what does this mean for the future of reasoning models?
That's a great question.
Like, are we currently bottlenecking our most advanced models by forcing their internal dialogues into plain English?
It really forces us to question if human language, with all its syntactic rules and ambiguities, is actually the optimal medium for machine reasoning.
Definitely something to think about next time you prompt a model to think step by step. Catch you next time on AI Paper Slop.